Hello, welcome to our Semiconductor education program. I'm Vincent Chang. In this lecture video, we're going to continue our series on analog integrated circuit design and investigate the output resistance of the bipolar Widlar current mirror or Widlar current source. Bipolar Widlar current source, part 3, output resistance. Here's the slide showing the contrast between the basic current mirror on the left and the Widlar current mirror on the right. The major difference is that on the right hand side you see the emitter resistance RE is included. On the left hand side, the output resistance based on our analysis and the explanation before is the individual output resistance, the output resistance of the individual transistor R2. How about the right hand side? That's actually the homework, the question I left toward the end of the part 2 video. And if some students, based on the intuitive analysis, maybe this could be the answer, right? This could be the answer, R2 plus RE. And I ask you, do you think this is right? And put down the answer. Do you think this is wrong? If you think this is wrong, and also explain why this is wrong, what's the key point? The answer is wrong. Before I explain why this is wrong and what's the right answer for the output resistance of the Widlar current mirror, let's talk about this first. Let me ask you another question. If this circuit, this mirror, is a DC source or AC source? Of course, what kind of question is that? It's a DC current source, right? So, for the DC current source, if we conduct the DC analysis, just as we did before, it's understandable. But why AC analysis? Why we need an AC analysis for a DC current source? For some students, some of them might be wondering, this is incomprehensible. Again, the question I raise to you is this. Why we need the AC analysis for a DC current source like this? Why? What is your answer? The answer is this. This is the key concept. We talked about before. Because you cannot find an ideal constant DC current source. Because in reality, the current source is not constant. Some current source goes like this, but some current source, others goes like this. Some current source goes like this. It's kind of flat, but it's not really exactly flat. But others is the pool like this. Because the current source is not ideal. It's the real constant. It's not real constant. It's close to constant, but it's not real constant. So we need a test. So how are you going to test? How are we going to test this? We send in, from the outside, look at the horizontal axis is VO. So we send in an AC output voltage and see the AC output current, how the AC output current is going to respond. In other words, we send in, like this, we send in an AC output voltage and see how the AC output current is going to respond. You got it? For the same output voltage, if the AC current, the responding AC current like this, that means you have the fixed delta IO, put this on your note. And the large delta IO means your output resistance is what? It's small. That's bad. That's poor. But if you send the same delta VO, the same output voltage variation, and then the delta IO, the variation of delta IO is kind of tiny, that means you have the fixed delta IO, but very small delta IO means you have very big, large output resistance. That's good. You got it? So that's why we need this. We need to measure the slope of the output transfer characteristic. Lower slope means the higher output resistance, the better. That's the key concept. So I want to make sure you have the solid understanding around this. You know what you are doing. So that's the definition of the output resistance, delta VO versus delta IO. This is why we need an AC analysis for a DC current source to measure how good this constant current source is going to be. The next step, we are going to examine the output resistance of this Widlar current mirror. Let's plug in the hybrid pi model, the second order model for the bipolar transistor like this. V pi, R pi, voltage control current source, GMV pi going down, and in parallel with the output resistance of Q2, RO. And then RE. And what's the third part? What's missing? The one on the left-hand side, the Q1 part, is the dial. That's the lesson we learned before. So what's the small signal resistance equivalent to this bipolar dial? The RE, right? And the R is being now short-circuited. So R is invisible on the left, on the real equivalent circuit because it's grounded. It's grounded. RE compared with R pi. RE is small. Compared with R pi, especially the bias current is different. The DC bias current is different. If the bias current is the same, usually R pi and RE maybe 100 times larger. But in this condition, you can still neglect the RE. RE is going to be very small compared with the R pi. So RE is negligible. So now the equivalent circuit, you are facing this equivalent circuit. Let me ask you again. Is the answer RO, intuitive answer, RO plus RE is good? No, it's not good. Why? Because you missed two things. Put this down on your note. Number one, you miss R pi. Number two, you missed a very important factor, the voltage control current source, GMV pi. You will see how the voltage control current source work later. You miss two things. So the intuitive analysis of RO plus RE is bad. So we're going to solve this because this is the first time. So how to solve this? Kick off voltage law. And then VT equals 2 drop. The first drop, the drop across RO. So pay attention, put this on your note. The current flowing through RO is what? It's IT, let me show you. It's IT minus GMV pi. So this current going down through RO is IT minus GMV pi. That's the first drop. And the second drop is minus V pi. This is the first drop across RO. And the second drop is minus V pi. So what is negative V pi? Negative V pi is this. It's this. Negative V pi, positive, negative. So here's the IT, right? So IT times what? The drop. This drop is what? The resistance is the RE in parallel with R pi. See this? IE times the resistance RE in parallel with R pi. In parallel with R pi, like this. So you need this, use this term, the Ohm's law, replace the negative V pi part. Then on the left hand side, you see all the VT, and on the right hand side, you see all the IT. The ratio is the answer. The ratio is the answer. The ratio between VT, the testing voltage, and also the testing current is the answer, gives you the answer. So it's much, much bigger than RO plus RE, right? Right? So let me introduce a one, because this is going to happen over and over again in the upcoming lecture. Conductance, transconductance times the resistance is a constant. It's a number. It's a number, one number. IC proportional to bias, RO inversely proportional to bias ICQ. Got cancelled. Early voltage divided by thermal voltage. The typical value for early voltage is 100 or 125 for bipolar integrated circuit technology. The typical value, therefore, the typical value for mu, put this here, all right? Just get the sense. The mu is very big, around 4,000 or 5,000. So it's a very big number. It's a very big number. So 1 is negligible. So another form, this one is exact solution. It's the accurate. And this one on the top, the one on the top is very good approximation. So therefore you see RO on the left hand side. Just picture this on your mind. On the basic contrast, in contrast to the basic current mirror is RO, right? Then now being multiplied by a factor. How big is the factor? Let's say if transconductance is, let's say if the transconductance is 10 and R pi in parallel with RE is also maybe 1 or 2 kilo ohm, then what kilometer? Kilo ohm. Then R got multiplied by 10 times or 20 times. This is what I just told you. I said on the left hand side is here, basic current mirror. Now on the right hand side is RO being multiplied by a factor, usually much greater than 1. Being multiplied by a factor. So I encourage you to take a screenshot on this, to put this in your mind, understanding, to remember the contrast between Widlar and the basic current mirror. So it's a high performance current mirror. Now let's move on to the next session. I'm going to spend a few minutes to talk about the simulation. Widlar current mirror. Widlar current mirror, simulation of Widlar current mirror. This is the code. And then let's do the DC sweep command, the sweep the VO from 0 volt to 10 volt, and get this. Get this. Here's the output characteristic. If you, so give us several concepts. Number 1, takeaway, constraint. To function as a normal current mirror, there is the minimum acceptable output voltage. In this case is what? It's about 0.2 volt. The red point, the voltage 0.193 is around 0.2 volt. It's around VC saturation, the constraint for the mirror function normally. Second, remember, second takeaway, it's a very good, it's suitable for IC, for integrated circuit, low DC, because it provides low DC output current. How low? This is actually the homework I left you in the first part video. I said, if the reference current is 0.73, now you see what's the output current? Down about 38 times, about 40 times. So 40 to 1, the answer is 18.9 micron. After you end this video, I want to stop and prove this, all right? I said try and error. This is nonlinear equation. The only way to do the hand analysis other than the simulation is trial and error. Trial and error. So remember, Widlar current source is suitable for a low bias design. Low bias design. Number 3, prove this. Based on the simulation, so therefore you can get the slope. The inverse of the slope is the output resistance. Try to reconcile this with the hand analysis. This is the homework I left you. 3 takeaway. 3 takeaway. Number 1, the constraint of the current mirror. Number 2, review the DC analysis. Number 3, try to reconcile the simulation result with the hand analysis. This is the end of the video. I hope you enjoy. Thanks for watching.